Hi everyone, thanks for the invitation. And yeah, so now I'll talk about alternating minimization algorithms. So finally we're getting to algorithms after all the invariant theory for all the problems that we've seen as well, like matrix, operator, tensor scaling, and we're going to see a little bit of their analysis as well. And feel free to ask questions, anytime. So this is joint work with half of the audience. So if you have questions that you feel shy to ask, just look around and find one of those people. Yeah, some of them are clustered here. And you can ask them. Otherwise, you can ask me as well. So, okay. So what are the contents? So I'll start describing just the alternating minimization that I guess like most of you know. And then I'll describe once again, since there's always that forgetfulness after lunch, right? Like the scaling problems. I'll describe the algorithms for them, and you'll see how remarkably similar they are. I'll give a general 3-step analysis to all of these algorithms. And then in the end, I'll describe a little bit like what else we need to do. A lot more hard work to get to the moment polytope question that Michael introduced in the past talk, okay? So alternating minimization, what is the usual setup, right? Usually you have a function f from some, you can think of maybe like convex spaces like x1 up to xd into R, and your goal is to find a global minimum, right? So you want to find an element x1 of the first space up to xd such that it minimizes your function. Right? So that's your goal. And what is the catch here? Usually, minimizing f in each block is very simple. Right? So Avi gave the example of like finding the minimum distance between 2 convex sets. Right? You can think of the 2 convex sets as x1 and x2, and you want to find the minimum distance. So, and what does that mean? That means that if I fix any of the d-1 of these coordinates, right, and I just optimize over one of them, it's very simple. It's easy. We know how to solve, and we want to find a global minimum. Okay? So what is the heuristics that we usually use? Well, we repeatedly just solve the basic problem on different coordinates, right? The heuristic is to pick the coordinate at a time, right? I just say, okay, pick the ith coordinate now, and then you pick the jth coordinate later. So we start with the initial guess of the solution and a time bound. We say, okay, we're going to run for a specific amount of time t. And then given my current solution, I choose a coordinate I. That's where the heuristic comes in. I find the optimum. And then I set the ith coordinate to that optimum. And then I while keeping all the order coordinates unchanged. And as long as I'm within my time bound, I keep going back and iterating. Right? Any questions about the setup? I guess it's familiar. OK. Now let's see alternating minimization into product group actions. Right? So the setup here will be the continuous groups, right? So my group G is the product of D groups, G1 up to GD, acting on a vector space V. For instance, you can think of the GIs as being like the special linear groups, and your V is the tensor space, okay? And the group action will be the usual that we're looking, right? Like, oh, this doesn't work. Okay, so does this work? Oh, this works. Okay, so the usual group action is, well, you have a tuple of matrices. It acts just as Ankit described in his talk, right? Like A1 acts on the first like slice of the tensor and so on and so forth. So, okay. Now, what is our input? Our input is given x, given a tensor x. What we want is to optimize the following function, right? Like, you pick an element of the group, and you want to find the element of minimum norm, right? This is the problem that Michael and Ankit described. And okay, so the goal is find the element of minimum norm in the closure of the orbit of x, right? So we want to find these matrices A1 star up to AD star such that they are close to the infimum, right? The element of minimum norm. Okay? And this element of minimum norm, the minimum norm we'll describe as the capacity of x. Okay? So the capacity of a tensor x is the minimum norm of the element in the orbit closure. Okay? So when the null-cone problem is obviously like x is in the null-cone of this group action if and only if this capacity is 0, right? Which means that you can drive the vector all the way down to 0. So this is our primal problem, right? Which is find the element of minimum norm. And now, well, as we saw in Ankit's talk and in Michael's talk, we have a dual problem, right? Due to the Kempf-Ness duality, right? Which is look at the moment map. And the moment map So, and now the dual problem that we're going to look at is the norm of the moment map, okay? So I pick an element X, and I define again, like for any group, any element of the group G, I'm going to define the Hx of G as the norm of the moment map at evaluated at Gx, okay? So, and the dual is what? I want to find, again, I want to find a group element that minimizes the norm, the L2 norm of the moment map, right? And the duality theory that Michael and Ankit presented is exactly what? And I'll describe the capacity here, this mu capacity, which is the minimum norm of the moment map, right? So Kempf-Nez is essentially saying the mu capacity of X, so you can approach this doubly stochastic if and only if your capacity of the primal problem is actually positive, right? So that's the duality theory that we have. Questions so far? This is just a review of the previous talks. So we're catching up for lunch. Okay, so let's see, again, let's review now a little bit of Avi's talk and see how does that get instantiated in matrix scaling, right? So in matrix scaling here, we have X is going to be a matrix with non-negative entries. And we say that this matrix is doubly stochastic if the row and column sums, they're equal to 1 over n, okay? So for example, I think my drawing will be, why is my drawing not appearing? Okay, so, well, here you can see a doubly stochastic matrix, but you have to, it's not normalized, I forgot to normalize. So it's equal to 1, but anyways, you can see a doubly stochastic matrix. And we say that Y is a scaling of X if there is dispositive elements, alpha 1 up to alpha n, beta 1 up to beta n, such that the entry Yij is exactly equal, I multiply the rows of X by alpha I, and I multiply the jth column of X by beta j, right? So, and we say that X has a doubly stochastic scaling if there is such a scaling Y of X such that all rows and columns of X, they're equal to 1 over n, right? So here's a matrix here, and you can see how this scaling brings this bottom matrix to doubly stochastic, right? But remember, the problem we're interested in is this approximate doubly stochastic scaling, right? So X has an approximate doubly stochastic scaling if for any epsilon you have a scaling of X such that all row and column sums, they're really close to being doubly stochastic, okay? And then the natural questions are, when does X have approximate doubly stochastic scaling, and can we find it efficiently, right? So far this is the setup, the most basic setup of a product group action. So, but this doesn't fit really like the image that Michael and Ankit were saying, because we need a vector space, we need a group vector and a vector space. So let's do the exact translation now, right? So as a null-cone problem, let's see the primal problem. That was the dual, right? Scaling to doubly stochastic. Let's see the primal problem. So here I have the group G, which is the torus with determinant 1, right? The special torus. So I have two of them, right? The row and columns operation. And it acts on V, which are complex matrices, by left and right multiplication, right? So I have the row scaling are the alpha i's, and the beta i's are the column scaling, right?
I just wonder if you really want the pointer, you can switch to the other.
Probably a good idea.
Yeah, because it seems like you want to use the pointer.
Yeah. You're right. Okay. I can point with this, right?
Oh, the other guy, the other pointer is not there.
It looks. Yeah, this is theirs, but maybe my computer doesn't work.
Why doesn't the pointer work?
Oh, I see. It has. Oh, okay. Now it works. Thanks. Okay, I had to switch it on. I forgot. Okay, so, okay, good. So, okay, so we have this group action, and now we will define the rows and column sums, right, as being the L2 norm of the row and L2 norm of the columns, right? So, and we're going to normalize because we want to go to 1 over n, right? So think of it essentially the same way as we thought in the previous slide. These Ri's are the row sums, and the Cj's are the column sums of X. And by Ankit's talk, we saw that the moment map was exactly, the moment map of X was exactly row 1 minus 1 over n up to row n minus 1 over n. So it's essentially saying the moment map is going to be 0 if and only if I'm in a doubly stochastic position, right? So our dual problem, again, is minimizing the norm of the moment map, right, which is exactly this distance to being doubly stochastic. Okay? So again, X is approximate doubly stochastic scaling if and only if this infimum is 0. Okay, so now our problem is I give you a complex matrix n by n, and is there scaling to the doubly stochastic? If yes, find it. And what is the algorithm? Well, Avi showed it to you. Right, the algorithm by Sinkhorn, repeat k times. You normalize the rows, so you make all the rows like 1 over n, and then you normalize the columns and you keep going. If at any point you get epsilon close to doubly stochastic, you output the scaling so far. Otherwise, you just keep going. Oh, and if you end, you just say no scaling. Right? If you never got close to doubly stochastic scaling after k times, you output no scaling. So the question is, well, suppose that we didn't see all this invariant theory before. First of all, are we making any progress at all, right? And the other question is, how do we know when to stop? How do we choose a case such that this algorithm is correct? And the third question, which I guess Akshay already asked before lunch, is there such an epsilon 0 such that if I can scale it to epsilon 0, then I can scale for any epsilon to doubly stochastic? I can tell you that any epsilon is possible, right? I can get as close as I want to doubly stochastic. So we're going to answer these 3 questions, yeah?
X is a non-integral.
No, I changed it to complex matrix because now I'm taking the L2 norms.
Also.
Yeah, to agree with your definition of the moment map, right? Your definition was like this. So, okay, now let's just describe the same, like a generalization again, right? So the quantum operator, which we already saw as well. So quantum operator is any map from positive PSD matrices to PSD matrices, right, which is given in this form. And the map is described by this tuple of matrices, of complex matrices, right, like Javier described yesterday. And then you have this operator T. T maps the matrix X to sum of AIX, AI dagger. And you have the dual of this map, which just maps X to AI dagger X AI. And again, as we saw, just recap from Monday, T is doubly stochastic if the identity is a fixed point of both maps, right? And again, a scaling of this operator, which I'm going to denote by a left and right matrix, consists of 2 matrices in SLN now. So 2 invertible matrices determinant 1, such that I multiply each of the AIs simultaneously on the left and on the right, okay? And again, if we follow the same template and we go to Ankit's talk, right? Ankit showed us that the moment map for this group action is exactly the moment map for the operator T. Okay, I'm going to interchangeably write T or the tuple of matrices A1 up to AN is exactly like T of the identity minus a multiple of the identity here, and the distance of the dual to a multiple of the identity, where alpha is just a normalizing factor. Okay, think of alpha as the 1 over n in the matrix scaling. So again, we have the distance to doubly stochastic, which is again the norm of the moment map. And again, we have that the operator scaling has an approximate doubly stochastic scaling if this infimum, the distance to doubly stochastic over all scalings, is equal to 0, right? So once again, the dual problem is the scaling problem, right? The dual problem is always the scaling problem, and the primal is the null-cone. So again, when we have the question, when can we scale, and can we find it efficiently? Okay? Now let me describe the algorithm that Gurvitz proposed, which was inspired in the first one. So sorry for the repetition, but they all look pretty much the same. So I give you an operator, I give you a parameter epsilon, and the question is, can I scale this operator T to epsilon close to doubly stochastic, right? And if yes, I want to find the scaling. So what Gurvitz proposed is to say, repeat k times. So let's left normalize the matrix such that T of identity becomes alpha I, and then I right normalize afterwards such that the dual becomes alpha I. So I fix the dual or I fix the T of I. If at any point we get close to doubly stochastic again, we output the scaling, otherwise output no scaling. And again, we have the same questions, so let me just keep going, right? Now let me describe the algorithm that the setup that Michael talked about in his talk. Now we have the tensor scaling problem. So I give you V is the tensor space, the space of all tensors of dimension n1 up to nd. And G is the SLN1 cross up to SLND. So you have invertible matrices determinant 1, dimension n1 up to dimension nd, acting again, as Ankit explained, on each slice of the tensor. And again, this is the action of G on X. And what is the goal here again? The null-cone problem, right? So the goal is usually, when I give you X, I want to find a group element, right, that gets me to the element of minimum norm in the orbit closure, right? I want to approximate the minimum norm. So the null-cone problem is, I give you X is in the null-cone, which is essentially the same as saying, is the capacity of X equal to 0? Okay? Now, what is the dual problem? So the dual problem, I'm just going to recap again. Sorry for the long recap from Michael's talk and Ankit's talk. If I give you a tensor, I'm just going to say any tensor is a pure quantum state. But in this case, I'm not normalizing, so that's why the asterisk. So, and you can write it as sum of X transpose, right, as a rank 1 matrix, PSD. So we know that the dimension is the product of these dimensions, and the trace is the norm of X. And like Michael explained, let rho I be the marginal of this matrix, PSD matrix rho with respect to the particle I. All right? We say that rho is d stochastic, or locally maximally entangled, if all of the rho i's are proportional to the identity, right? Similar to the operator scaling setting. And, well, quantum distillation problem is, if I give you a pure state rho, is there a scaling of rho into d stochastic scaling? And again, from Ankit's talk, we saw that the moment map for this tensor action is exactly the distance of the marginals of X to the d stochastic state, right? So again, the dual problem becomes, once again, no news, right? Finding the minimum distance to the minimum norm of the moment map, right? So again, what is the tensor scaling algorithm? It comes with no news, right? I give you a tensor, a parameter epsilon, and now again, I start with an input X and the identity scaling, and I repeat k times. If I'm far from d stochastic, if I'm close to d stochastic, I output the scaling. Otherwise, find me a marginal, right, which is really far from being the ith stochastic, right? So then I normalize the marginal, and I keep going, right? I keep picking the marginal that's furthest from being identity. Otherwise, I output no scaling, okay? So again, right, same algorithms, same questions, right? How do you know when to stop? And is there an epsilon naught such that if I can scale there, I can scale everywhere? Okay, so what is the analysis for this algorithm? Okay, it's quite simple. It's these 3 steps. So in the beginning, think of any of the 3 algorithms, matrix scaling, operator, or tensor. In the beginning, we start, our input is a matrix with integer entries or Gaussian integer entries, okay? So its norm is bounded, right? So if there are integer entries with bit complexity b, the norm of X is bounded by some polynomial in n, right? The dimension of your input plus 2 to the b. So this is trivial from the input data. And now what we need to show is that if we're really far from d stochastic, or more generally, if we're far from the solution to the dual problem, right, then normalizing X decreases its norm by a factor which is exponential in epsilon over n.
Normalizing in any coordinate.
Normalizing in any coordinate that's far, yes. So the question is here, any normalization for any bad coordinate, if you make it become good, it decreases the norm of X by this big factor, which means that we make significant progress in the primal problem, right? And this follows from a quantitative version of AMGM, so this is not, we're not going to break too much of a sweat doing this. And the hard part in general is to prove this lower bound, which is, you know, if the capacity of X is bigger than 0, which if X is not in the null cone, then the vector of minimum norm, then the vector of minimum norm is really large, right? Then the vector, the norm of the minimum norm is large, okay? And to do the lower bound, we need some properties of the invariant polynomials. We need to show that the invariant polynomials are generated by nice polynomials. And what do I mean by nice? Nice, I mean just polynomials with integer coefficients which are not too big, okay? Yeah?
For polynomial convergence, it's sufficient that you have an exponential lower bound capacity.
Right, yeah. So yeah, obvious right. So and I mean, usually we prove these bounds, so that's why I put this 1 over n squared, but obvious right, that like in general, you can prove weaker bounds. If you prove that this capacity is bigger than 1 over exponential in n, we still make enough progress, right? Because every time if we're far, if we're always going by a constant factor, right? We're always making constant progress.
So in this tensor setting, we cannot prove this.
Yeah, in the tensor setting.
No, we proved that the problem with the tensor set is for the null-cone is the epsilon that's the problem, right? Like we need to be really close to yeah, we prove exactly because of your paper with Christian, because the invariants are really nice, right? Like, but if you use Cayley, then you have a problem, so we'll have something better, yeah.
Okay, in general, for polynomial analysis, it's
Yeah, right. Yeah, what I've been saying is right. In general, you just need 1 over exponential in n here, and you would be good. But for these 3 problems, we are able to prove better, so I put it here, but you're right. So, yeah. Okay, so if we're only interested in the epsilon scaling problem, if you give me epsilon as a parameter, this analysis shows that the running time will be, sorry, any question? Oh, that show that this analysis will take a running time of polynomial of nb over epsilon, right? So if you give me the epsilon that you're happy with, then we're good. But to solve the null-cone problem, then you need to prove that you need to pick a big enough epsilon. And how big? Well, for the matrix and operator scaling problem, we'll see that this epsilon, if you pick epsilon to be 1 over n in general is enough. But for the tensor scaling, you'll see that the only bound that we can prove is actually epsilon minus exponential. And then this is pretty bad, right? That's why to solve the null-cone problem for the tensor scaling action, we take exponential time. Okay, but we'll see this later with more detail. So, so any questions so far? Okay, so let's see how to analyze these algorithms now with this 3-step approach. Each of the algorithms, so we can get ready for the hard stuff, right? So, okay, here's the algorithm again for matrix scaling. So how do we analyze? Again, we have an upper bound, which is really easy just because x is integer with bit complexity b. Again, the AMGM shows that x shrinks a lot. And now, here comes the hard part, right? Like what LSW did is that the permanent, and I'm writing this y hat matrix here to say like if x has complex entries, just x hat will be, each entry instead of being xij is the norm of xij squared, okay? So which is the corresponding to the non-negative matrix, right? So, right, so at first, you know that x is a matrix with integer entries, so you know that the permanent of x, if it has a matching, is greater than or equal to 1, right? Which means that the permanent of any scaling of x is also going to be greater than or equal to 1, which means in particular that the norm of this vector y cannot be too small, right? So that's one way of showing it. And that's what they do in LSW. And then, you know, you get your scaling, right? Within nb over epsilon time, okay? So, okay, and we know that like this permanent, if permanent is bigger than 0, if and only if you have a matching, right? So this algorithm is correct, right? Now, you know, just aside here, the permanent here is not really needed, right? As any monomial encoding the matching in the adjacency matrix would work, right? So here they use the permanent, but if you're talking about invariant theory, we would say, well, you know, if x is not in the null cone, I only need one polynomial which generates the invariance, not to vanish. And which polynomial would be is any monomial that encodes the matching, right? Encodes the matching for which x doesn't vanish, right? So that would be like a more refined approach. Okay, any questions so far? Okay, so now let's go to the operator scaling case and the analysis here, right? Again, we have the algorithm. And again, the analysis is pretty much the same, follows the same template. So at first, my operator has L2 norm as a vector, right? Like polynomial in n and 2 to the b, because the matrices AI of the operator, they're integers with bit complexity b. Again, we use the AMGM the same way to show that if we're far from double stochastic, we're going to shrink the norm. And now we know that there is if t is not in the null-cone, right, you can find one of the invariants for which it does not vanish, right? And if it doesn't vanish, moreover, these invariants have integer coefficients. So if they don't vanish, I'm missing a norm here. So there should be a norm. The norm is greater than or equal to 1, and it will be bigger than or equal to 1 for any scaling of t, right? And therefore, we can obtain a lower bound on the norm of t for any scaling. So, you know, we cannot shrink forever, and we're going to get our scalings. And I forgot to put to write the invariants here, but Avi wrote the invariants back then, which was determinant of AI tensor xi, right? And is there a chalk there? Maybe, should I write there, the invariant? Or?
You can write it.
Maybe people can see. Okay, so how do we prove that there is a nice invariant? I guess I can just write here. So we know that the invariants, they are determinant sum of yi tensor xi. So these are, can everyone see? I guess it's. So these are determinant of sum of yi tensor xi, I going from 1 up to m. And these are polynomials that, so what we prove is that when you plug in AIs here, there exists a choice of y for which this polynomial doesn't vanish, right, if you're not in the null-cone. But now how do you choose this y, right? The way to choose this y is by Schwarz-Zippel, because if you fix AI here, this becomes a polynomial in the yi's, for which you know that this polynomial is non-zero. So if it's non-zero in particular, when you apply any random, when you substitute the yi's by any random value, you get a non-zero polynomial, right, with high probability. So there exists one, and Schwarz-Zippel shows that you can take these yi's to be matrices with integer coefficients, which are not too big, okay? So that's why these p's here in step 3, they're actually nice, okay? So now, you know, we still have not answered this question of the epsilon naught, which I'll push to the end, but.
So the point is that what you want of P is two things, small degree
Mm-hmm.
and small coefficient.
Right.
That's what is used in the low bound.
Exactly, yeah. So the main point here is exactly. The only thing we need from P is that P has small, like integer coefficients, and they have to be small, and the degrees of P that you need to take, they're also small. I mean, in this case, we don't really need, right? We only need finiteness, but in general, you need in general, what you want to have from P is small degree and nice and small integer coefficients. These are the only two things.
You should be careful because if you don't use the degree, the random thing does not work.
That's true. That's true.
You have to be careful with choosing the guy.
No, so it is sufficient that it has small coefficient and small degree in order to bound the norm. One way to get a small coefficient in this particular case is knowing that the degree is small. This is one way in this case. You don't need it, in fact, as we discussed, but
Right.
that's only one way. But in general, this analysis of the lower bound just requires that some invariant, that the invariant polynomials you look at a small degree and small coefficients. This will apply the norm law.
When you mean smooth, you mean smooth.
Small, it means the polynomial bit complexity. Yes.
Right.
This is, I mean,
So the coefficients are exponential size, but the bit complexity is polynomial. Yeah, I agree as well. There's the catch that if you don't require the degree bounds, you have to prove that they're small in a different way. Yes, that is true. Yeah, thanks. Okay, so now let's talk about the tensor scaling algorithm, right? So again, we're going to follow the same template. So I have my tensor with Gaussian integer entries. some parameter epsilon, and I want to scale to doubly stochastic, right? So what is the analysis again? Well, the norm of my tensor is bounded, right? Just because I give you as an integer input. Again, the AMGM follows the same way, okay? So I'm not going to describe it. And then here again, we need this P to be this invariant, which has degree exponentially bounded and also like exponential bound on the coefficients, right? And so if you have that, you know that P of x is bigger than or equal to 1, and it will be greater than or equal to 1 for any element in the orbit, and therefore you can use this fact again to give a lower bound on the minimum norm, okay? And the lower bound will again be 1 over n squared. Okay, so again, this is the same way verbatim, the same analysis as the operator scaling. Yeah, and here I guess I described more carefully, right? So here, the invariant ring here is generated by polynomials of exponential degree by Dirksen's result, and integer coefficients of, the norm is here is exponential, but because of the works of Procesi and Burgesser and Nickemeyer, we can prove that they have norm actually bounded by polynomial n, this polynomial n to the degree. Sorry, I forgot that. Okay, n of the degree of the polynomial. So be n to the 2 to the n squared, I guess. Okay, so that's what Avi was saying. We need a bound on the degree, and we need a bound on the size of the coefficients. Okay, good. So, yes. Okay. Here's the proof, right? Like, yeah. Anyway, so that was the bound that we needed, and
this is just a calculation.
This is just exactly.
This degree bound and this coefficient bounds are sufficient.
Exactly. This is just the calculation. So yeah, exactly. Now, the only question that's left is if we want to solve the null-cone problem, which epsilon should we choose to solve the null-cone problem, right? And then here, okay. Right? So here, let's go to the tensor scaling, which is the more general, and then I'll explain why the matrix scaling and the operator scaling, the bounds are actually much better, okay? But let's start from the more general case here. So we have this algorithm, and the only thing left is to pick epsilon, right? To decide membership in the null-cone. So how are we going to choose this epsilon? Well, we're going to use this instability criterion of Mumford, which says, remember, Ankit mentioned in his talk that if we can drive an element to 0, right, we can do it so with a one parameter subgroup. And what Mumford did is he asked the question and he answered, so how quickly can we drive it to 0, right? So we're going to see that he gave an instability parameter, which is a parameter that just measures how quickly can I send a point in the null-cone to 0 using a one parameter subgroup. And then we're going to use the work of Ness and Mumford that they show that instability, this instability parameter of Mumford actually lower bounds the distance to d stochastic, okay? So the norm of the moment map, okay, for any x. And therefore, if we can give any lower bound on instability, okay, which is essentially a lower bound on the solution to the NP, to an LP problem, to a linear programming problem, then it implies lower bound on the dual problem, okay? Because remember, we already have lower bound on the primal. We already showed that the capacity is lower bounded using the invariant polynomial, and now we need to use this criterion to show that the dual is also bounded. Yeah? Okay. So, any questions here? Or okay. So, oh, I see. Don't read this. I don't know why it's showing up. I guess I forgot the animation. But okay. So again, Hilbert-Mumford criterion, right? So if I have x in the null cone, if and only if there exists a one parameter subgroup such that the limit, it drives it to 0. Now, how quickly does it go to 0? Well, let's look at the one parameter subgroup again for the tensor action, right? So the one parameter subgroup, as Ankit mentioned, can be given by this bi minus 1, these diagonals. So this is only the ith element of the tensor action. It is given by a diagonal of t to some integers, right, which sum to 0. And bi's can be any unitaries, right? So if you can drive to 0, Hilbert-Mumford just shows that you can drive it like this. And now, let's look at the support of the tensor after you act on it by these unitaries, B1 up to BD. Okay? And what is the support? Is you act by the unitaries, you rotate the tensor, and now you just look at the coordinates in which the tensor is non-zero. That's the support of the tensor. And if I'm driving this tensor to 0, it means that for every index in the support, it must be that my t will have a positive exponent, right? My t will be raised to a positive exponent, right? So then I must have these constraints, okay? So what Mumford did is, well, let's define the instability of a tensor as the minimum over all the elements in the support of the exponent of t, right? So we're always bounded by this lowest of us, right? So I always go to 0 based on this lowest guy, right? So that's Hilbert's instability parameter. And now we only need to show that if I'm in the null cone, my instability is high, right? And we also need to show that this lower bounds the distance to the double stochastic, okay? So any questions so far? This is good? Okay, so, and the instability for x, right, is simply the maximum over all one parameter subgroups of the instability of lambda x, right? So I want to know how fast I can go, I might as well pick the best one parameter subgroup. Okay, so so first of all, how do I prove a lower bound on the instability in general? And then let's show how we can use the instability to lower bound the distance to double stochastic. So remember, if I have a one parameter subgroup that drives it to the null cone, it implies that the following linear program has a solution. What is the linear program? Well, it's just the constraints that I input on my one parameter subgroup from the previous slide, right? So I need my sum of aij's to be equal to 0, right? Because I'm working on SLN, so my determinant is 1. And I mean, I just need the sum of my aij's for any element in the support. Remember, I had the requirement that this was bigger than 0. But if it's bigger than 0 and is integers, right, as Ankit showed, it has to be greater than or equal to 1, right? So if I find any solution to this linear program, right, this corresponds to a one parameter subgroup that drives it to 0. Now, a simple result in linear programming theory just shows that, like, based on this linear program, on this description, it has a solution bounded by exponential minus n log n. Okay? So you can always show that such a solution exists if you have one. Okay? And this gives an upper bound on a lower bound on the instability. And now, how does instability lower bounds my distance to doubly stochastic? So, okay, now, here's the thing. Suppose that I just gave you the tensor x, and let's forget about the unitaries first, okay? Let's just forget about the unitary transformation. Let's just see how does the distance from doubly stochastic of x is lower bounded simply by just trying to drive x to 0 just using action on the tori, okay? So I'm not going to do rotations of x, I'm just going to apply the tori in x. So it's easy to show, I mean, it's an easy calculation, but not very illuminating to show that, you know, for any aij, which is a solution, you can show that this quantity here, the instability parameter, lower bounds the distance to doubly stochastic, okay? It's a simple calculation, not very illuminating. And then the only thing you need to show now, right, is that, well, remember, this distance to doubly stochastic is invariant, right? Is the norm of the moment map, which is invariant under unitary transformations, right? Therefore, this distance here is equal to the distance of any unitary action, right? So then when you put together, right, in particular, this distance for any element in the orbit, right, will be less than or equal to this quantity, to Mumford's instability parameter. So that's how you get a lower bound on the distance to doubly stochastic. Okay? And I mean, the result of Ness and Mumford just holds for any really nice group action, as Ankit was saying, right? Therefore, what we get is that the distance to doubly stochastic from x is greater than or equal to the instability of x squared, and by this very general bound that Schreiber gives, we can lower bound it by inverse exponential, okay? So if my epsilon is inverse exponential, I know I'll decide membership in the null cone. Okay?
This gives an exponential time algorithm for the Null-cone problem in this very general setting.
Exactly. This gives an exponential time.
And the previous algorithms that existed, I guess, were doubly exponential.
Right. Yeah. So before this work, the previous algorithms that gave membership in the null-cone, they used Grobner basis and Grobner basis theory, and they were doubly exponential, right? Yeah. And there's a simple also algebraic algorithm, right? That now, if you use Dirksen's bounds on the degree, you can simply compute all the invariants in exponential time, and you can evaluate them in exponential time as well. So it's a different algorithm for this problem.
I don't think it works for Tensor. It works for this gives you a linear system of exponential size of the solution there.
No, so you have a polynomial. You look at all the invariants, right, up to degree like 2 to the n squared. And then you evaluate x on all of these invariants.
They are doubly exponentially many. Or they are just, because n is small.
Right, exactly. Yeah, only exponential.
Is this like something like integrality gap? So in the case of the scaling, it's big because of Hall theorem.
Yeah.
And here, and ultimately it's some kind of unimodularity, but you don't need it. So I actually had this situation when you don't deal with Newton polyton.
Uh-huh.
In general, so again, the problem is in general because this to check whether Monod integer vector is there. So if there is a big gap, you can do it. But in general, this is what you get.
Right, exactly. Yeah. In general, this is what you get. And now, I'm going to talk about the matrix and operator scaling, right, which is what you do. Yeah, not for hyperbolic polynomials, but you're right. So now,
It's almost the same.
exactly, it's almost the same. And now we're just going to use the Hall condition to give a really easy solution to the problem, right? Because remember, okay, if you look here, to lower bound the distance is doubly stochastic, I only need to show that this linear program has a really nice solution, right? But if I can give a really good bound on this solution, on any solution to this linear program, then this bound I can substitute it lower bounds the instability, because the instability is the maximum over all of these, right? So how do we get better bounds in the matrix and operator scaling? Well, now the only thing we need to do is we need to construct a big solution, right, to this problem, right? We need to show that, this is too general. This applies to any linear program of this description, right? But for matrix and operator scaling, if we want the polynomial time algorithms, we have to show that we can do better. And what's the hint? As Leonid already said, let's just use a Hall blocker to find a small solution, okay? And if we find a small solution, we can show that the distance to double stochastic here is 1 over n squared, right? So how do we do that? Let me just show you how do you use the Hall blocker to find a small solution. Let me just show you the example in matrix scaling, and by picture you figure out how to do it in general, right? Suppose that I have this matrix that Avi showed in the previous day. You can see the big block of zeros. So what do? Well, whoa, it disappeared. It's not supposed to disappear. Okay, so it would disappear. But you know what it is. You've been drilled on this matrix now. So now the scaling is the following, right? So wherever you have the block of zeros, you can put the t to the negative powers, right? And whenever you need to make things vanish, you put the t with really high powers, right? So in this case, you only need to take powers up to n, and you're done. So here, remember, if I look at this matrix, I need to make the first row and the first column disappear, right? So then I put the first row, I make it disappear here, first column, I make it disappear, right? And then the rest I can just fit in to make the determinants to be equal to 1, right? And now everything disappeared. Okay, so, how can Leonid also generalize this to the operator scaling? Well, it's quite simple. He just uses his description that if you're in the null-cone for the operator scaling, all the matrices have a common Hall blocker. So if they have a common Hall blocker, you can just make one vanish, and you make all of them vanish at the same time. And that's why we have this kind of somewhat miracle that operator scaling also has this really, it really requires just a large distance from double stochastic.
The common Hall blocker is the shrunk subspace.
Exactly, the shrunk subspace, yeah.
Which gives a change of basis to the diagonal.
Exactly. So the shrunk subspace gives you exactly this common Hall blocker for all of them, and therefore you just do the same idea, right? So you have bigger bounds. Oh, okay, this is going much faster than I thought. Okay, I guess everyone's super drilled on invariant theory that this becomes easy. Okay, so now, then let's talk about non-uniform marginals and see what problems will arrive here. What else do we need to do? And it turns out we need to do quite a bit more. So here, what's the setup? I give you a tensor, and now I give you as a pure quantum state. I'm going to normalize it. I'm going to work on the projective, in the projective space. And we can write this tensor as, again, rank 1 PSD matrices with trace 1. And again, my group G, instead of being SLN now, because I want to get rid of that annoying minus identity, my group will be products of GLNs now, okay? Acting on the projective space. So again, recalling from Michael's talk, the quantum marginal problem is given a pure state X and my target marginals, rho 1 up to rho d of unit trace, is there a scaling of X that has such marginals, right? And again, Michael showed that this is essentially membership in the moment or entangled polytope of X, which I guess Matthias will talk more about. And if you look at these vectors pi, which are the eigenvalues of these of the rho i's, is essentially saying, does P, the vector P of all of this spectrum, does it belong to the moment polytope of X, right? That's from Michael's talk. Nothing new here. And what is the natural attempt here, right? We've been for 50 minutes now talking about scaling algorithms to uniform marginals, and now we throw in like different marginals, right? So is there another representation where the moment maps for the image of X is given by exactly rho I, the marginals of X, minus these PIs, right? Let's just reduce to the problem that we know how to solve and love, right? So, okay, and how do we do this? Again, from Michael's talk, we can do the so-called shifting trick, which, yeah, it wasn't there, but I noticed there was no extra slide. But yeah, so there's supposed to be, sorry, but so if I take the spectrum of the marginals that I have, or my target marginals, it was there yesterday, but it was on the slides yesterday, but it's not there today. But okay, so.
You have time to explain it slowly.
Oh no, Michael, here. Come finish. I have your old slides. Eh? Okay, so essentially what Michael would have thought that, well, he taught me, is that there is a, if you have the spectrum of the target marginals, and if I look at the spectrum as some integer Li over k, then if I look at this tensor y, which I define by just blowing up x to the power of k, I take the kth tensor power of x, and I use this highest weight vector with respect to the dual of L, okay? Then when I look at the moment map on the tensor y in this larger space, okay, what happens is there is this shifting trick that you can look at in the paper now, that it converts the moment map of the tensor y is exactly k times the moment map x plus the moment map of the highest weight vector of L dual, okay? But it turns out that the moment map of this highest weight vector is exactly L dual, which is just minus pi, okay? Minus pi, not minus pi, sorry, minus Li, okay? And therefore, if we use the shifting trick, we can convert a problem in arbitrary marginals essentially to a problem of mapping the moment polytope now instead of to the target marginals, I map the moment polytope again to 0, right? Which again means uniform scaling, right? So non-uniform in this small space means uniform, mapping this to uniform in this larger space. Okay, that's the whole like punchline.
It does not look uniform because you have pi rather than I.
Right. Yeah, but I mean by uniform I mean you only want to map to moment map 0. That's what I mean by uniform problem. Yeah, uniform problem is I want to map the norm of the moment map to 0. Sorry. Yeah, it doesn't look uniform, but it is kind of uniform in the same way that we have the same dual problem. Yeah, thanks. This is not intuitive here.
Because there is a different way, a different type of reduction where this non-uniform scaling problem is reduced to a uniform scaling one.
Right, right.
Which you are not talking about.
Which I won't talk about, exactly, yeah. There's a different, yeah, you're right. Okay, now, okay, so this, now we reduce the arbitrary marginal problem to the uniform case, but you have to take this with a truckload of salt, not just a grain of salt, because there are a lot of caveats here that we're going to see now, okay? So we're going to see exactly when we try to come up with an algorithm for it, okay, and try to analyze. So I'm going to explain a little bit of all the caveats, okay, because we're still going to run our scaling algorithm on X, okay, that's one of them. We're not going to work on this big space. We're only going to use this bigger space for analyzing the algorithm in the original space. That's the first caveat, okay? And we need to scale X now. We cannot do any scaling on X. We have to scale X by a subgroup of GLN, which is the Borel, okay, which we'll be explaining in a little bit. The other caveat is that I cannot start just with X. I have to start with the generic element in the orbit of X. So, you know, there's another caveat. And yeah, and the capacity won't be just the simple vanilla capacity. We'll have we'll have an extra term to it. So, which I won't get into too much detail here, just to not overload everyone with information. So, okay, so what is the non-uniform tensor scaling algorithm now? Is exactly what you would expect, right? So I start with input X, and now I need this random scaling G, which I'll explain why we need this G later in the analysis, okay? I just pick a random scaling G of X. So I essentially start with the element G acting on X, okay? That's my random element in the orbit. And now, instead of having the distance to doubly stochastic, I have this distance to my target marginals. As long as the distance to the target marginals, if it is small, I have the right scaling, so I'm done. Otherwise, again, pick the marginal which is furthest away from this target marginal, okay? And then normalize this marginal, like fix it, right, correct it. Now, when I correct, I have to correct it by an element of Borel, okay? So I need to choose this Ri. I cannot scale by any element. I need to scale by Ri being upper triangular, okay? And I'll explain why in a little bit in the analysis.
Maybe a comment.
Yep.
I think we use the blended combination ds for distance to stochasticity, but here it's just distance. Or do I?
No, yeah, no. There's distance to stochasticity, but there's this p here, and the p is exactly is the distance to my target marginals, right? Before my marginals were uniform. The target marginals. You would just wrote ds, exactly. And now that we have like distance to this target marginals, I put this p there to make the difference, yeah. Yeah, so you should, yeah. Okay.
So it's sort of lucky that we can take the square root of rho I in many ways, and in particular
In upper triangular way.
It was not used or even thought of in previous ones.
Right, exactly. Yeah, yeah. It's interesting to notice as well. Yeah, this is really interesting that, like, well, it's lucky that we have this upper triangular factorization, because before in the operator scaling, right, we just took the square root of the PST matrix. Yeah, this would also work. This will work. This will work. Yeah, this will work, but we never thought of it. It was not necessary, right? So we just did. It works with any square root, right? Like for the operator scaling.
You just don't need square root at all. You can have completely rational operation.
Yeah, you can. No, but this is a different.
Yeah,
you're right. But this is a different issue.
Yeah.
There were many
Yeah,
scale the particular component in the operator scaling. Also here there are many ways, but there it works with any, and here it works with just this one.
Exactly. Here we only know how to make it work with the Borel. We don't know how to make it work with anything else, right? So yeah, but you're right. I'm not even talking about bit complexity today. You're right. I promised to talk about algorithms, but these are like fake algorithms, right? So yeah. Okay. So what is the analysis? And let's see what comes complicated. Borel is upper triangular. Yeah. Okay. So, Okay, so and how do we do the analysis now? Now, remember, in all the other problems, the first step was super trivial, right? We just had the input, the norm of the input was upper bounded, and we were happy. Now, even the first step is not trivial, right? So in the beginning, remember, we chose this G0, this initial random element, right? But we need to show that this initial random element is actually small, because we need to start off, again, remember, with a tensor of small norm, right? So in the beginning, and then there's this k here, which is the degree of the highest weight vector that doesn't vanish. So to begin with, we already need Dirksen's degree bounds on the highest weight vectors to show that this G0 is nice, okay? And once you show that this G0 is nice, that there is a highest weight vector that does not vanish on G0 x, then we can use Schwarz-Zippel to get a bound on the entries of G0. So G0 is a group element which has the small integer entries, okay? So, and now, the progress per step, right? Again, the progress per step, we still use the quantitative AMGM, which is a little bit fancier now, but still not very hard. But the issue that we need to do here is, remember, we have an invariant. The highest weight vector is invariant. But is invariant under which group action? Right? So is invariant under Borel, not under all the groups. That's why Avi was making the point that here we only know how to make it work with Borel. Because we need to maintain the fact that the invariant is preserved, because we need the lower bound on the capacity. Right? So we need to show that every time we do the scaling, it remains invariant under the Borel.
This is a ds sub p now.
Oh, yes, this is ds sub p. Thanks. I asked for forgiveness before, but you won't give it to me. It's okay. No. Thank you. I'll fix it. Yeah. And again, the lower bound now, there is this different capacity, okay, which I won't describe, but we again can show by the similar step as the tensor scaling that if this capacity is bigger than 0, it will be still bounded by 1 over n squared. Okay, just because we can construct really nice highest weight vectors. Okay, so. And this completes the analysis, but you can see now that all the steps are getting complicated. So, yeah, and yeah, this is it. So, any questions here?
Maybe just.
So earlier you just looked at some invariant vector demand,
Right.
Now you somehow seem to want to just look at highest weight vectors.
Right.
Is this in some sense special or?
Right. So, yeah.
The general polynomial will get useful to, if I give you some polynomial that has a nice description that doesn't match, but you can get me highest weight vector that doesn't match.
Right. So the highest weight, the highest weight vectors, like as Michael mentioned, they're polynomials, right? In a different space, in the space of the y tensor, the highest weight vector, right? Oh, sorry, the x tensor k to the.
No. My point is, initially you were looking for some invariant polynomial that doesn't vanish, which has small degree and small coefficient and so on. Now you're saying you don't want some invariant polynomial, you only want to look at the highest weight vector. Okay, so my
Invariant polynomials are the special case where the highest weight is all zeros weight. So that's the relation.
I see.
So the uniform scale.
No, but you take some other vector in the representation. Or do you really need it to be the highest weight vector?
I'm not sure.
Is this question about the shifting trick that?
It gives a representation, there's an irreducible representation corresponding to this.
Right.
So is it necessary that you take the highest weight vector, or can you just
That's exactly what it is. Sorry.
No, go ahead. Yeah.
That's exactly what the G0 comes in. So in a sense, because you have this G0 going on, you're really probing the entire representation. I think that is not
Right.
not special. But it's nice here, like here, if you choose highest weight vector, it matches nice with these upper triangular scalings. If you choose the lowest weight vector, you would do lower triangular scalings and so on. So there is a relation in this sense. But really, you extend, you're going from this trivial, from this one dimensional, you reduce it to now a larger one.
Right.
That makes everything much more interesting.
Yeah, there's another point to make which is related, that this is only a probabilistic algorithm.
Right.
We don't know, because of the first step, we don't know how to remove this randomization.
Right. And yeah, it's a lot of randomization here actually, right? Because this we use actually polynomially many bits as opposed to logarithmic many, like polylog. Yeah. Okay. So, and I guess this was everything. So, if there's no more questions.